Thank you very much for the nice introduction. Okay, so this talk is phrased as a question, right? And I'm not sure if I'm going to answer it, but let's figure it out together. That's the point of the talk. So AI coding, right? I bet a lot of people have been talking about it. How many people are doing it today? Hands up, right? Most of the room. Whether we like it or not, that's another question, but I'm not going to ask that. How many of you have an existential crisis about that actually replacing your job or kind of making you do different things than you were before, and you kind of feel uneasy about that, right? And well, I went through all of the 7 stages of crisis, and I think I'm on the upside now, and that's what basically this talk is about, right? So, well, if we look at it, we have now agents can code and whatever. So it doesn't mean I just kick off an agent and go to the beach or out of office. Maybe not. If history is anything to go by, it's more like now I have like 50 agents running at the same time, and I don't know where to look, and all of these things. Because every time in history so far that I can see, when we've freed up energy or time to do something else, then we just find another thing that we do better or improve or something like this. And the question here is basically, if we free up time from coding, can we now use that time to, for example, formally prove things? Because the cost-benefit equation has changed for that. And by the way, these illustrations are made by my girlfriend Katarina Jakobsson. They are very nice. You're going to see more of them today. I was so happy to do this. It's bringing so much life to this presentation. So you might be familiar with Jevon's paradox as well, which basically states, or it's come from the 1900s or something like that, where the observation was that when kind of steam engines and stuff like that became more efficient, and they didn't need as much coal as before to run, then you could imagine that the amount of coal consumed will go down because we're going to run as many trains as before. And when we do that, we don't use as much as before, right? But what happened actually is that now that things became more accessible, more cheaper to do, the actual resource consumption in total went up. So I'm not sure if this is going to hold this time. No one knows. But if it does, it means that we're going to just have more software engineering hours put into all of this because the cost is going to go down, right? And yeah, let's see how that goes. But if it's true, we're going to have tons of more software. And that's kind of scary, right? Like, it's already, software already has bugs and these kind of things, and we're figuring out how to deal with them. And it really brings the question of, kind of, I think about my father when he studied to become a forestry man 35 years ago. He graduated just around the time where forestry machines, became the thing, right? So like you studied to do the manual labor, but then now you had a machine instead that did the job for you, and you needed to upskill to do something else. We now have a forestry machine, clearly, that does the work for us and chops down the forest better than we could do ourselves. But how do we drive the forestry machine? I don't know. Predicting is hard, especially about the future, but let's, take a stab at it. There's a couple of other problems with AI coding as well, as you might have noticed. Even in the age of AI, beyond the hype, we still have some amount of responsibility towards society, right? We can't put, all kinds of crap out there at the end of the day. And if the part I'm uneasy about is like, if we stop understanding the code, what happens then? And how do we still get some assurance about what's happening, even though we somehow wouldn't understand the code? That's kind of interesting. Also, any large software project like Kubernetes or similar has a lot of inertia. So like any change you make to it takes a ton of effort to do, because the probability of breaking something is huge every time you try to improve something. So this goes for all other coding as well, right? So like at some point where the probability of breaking something is much higher than improving something, what will happen then? And I really like this Chef Rosell, like she's a long time contributor to the cloud native space as well, rule of only new mistakes allowed. How do we prevent the old mistakes from happening again in a rigorous way, not just adding one unit test in some place and forgetting about it? So we have lots of questions. Yeah, I have been thinking about this for a while. At the moment, I'm a staff software engineer at Upbound, and this is through the lens kind of CDAR policy, which is a new CNCF project, which is an access control engine, and it's formally verified. And they applied some of these methods, and it's pretty interesting how they're doing that. And yeah, I'm graduating from Malta now as well, finally, so I can spend some time on some of this else. After 10 years of these kind of stuff. So when you ask this to people, right, like they will say outcome engineering, they will say spec-driven development, and I think that's great, right? Now it's just like Kubernetes let us, focus on end goal. Like we want to have, 5 pods running, right? That's what I want. I don't want to figure out how to create those. We can focus on the end goal in a declarative way. And it's great because, as we know, as we start writing stuff down, it really shows how much we didn't think about when we had it in our head. And in the words of Leslie Lamport, thinking doesn't guarantee that we won't make mistakes, but not thinking very much guarantees that we will make mistakes. So that's great. That's a good start. But what is the language? So if we just write this in Markdown files, if we write them in Markdown files, then natural human language is very ambiguous, as you might have noticed. It's very easy to say something that is nonsensical, but it's hard to pinpoint that this is nonsensical or contradictory from here and here, right? And if you get that, then you get very non-deterministic outcomes, right? Like when you put a contradictory statement to an AI agent, I don't know, like I guess it flips a coin or something. So can we use mathematics for this, right? Let's see. So this kind of ladder, if we look at it from the, as a roadmap of what you could do, because luckily there's been a lot of research in this area, for 100 years or 70 years or something in the history of computing. And if you ask any, senior engineer about like, should we make this feature then, or should we add these lines of code, then it's probably no, if we don't need them. So first, let's not make code that we don't need. If we have to do it, then let's start with abstraction. So let's limit kind of what bad can happen, right? For example, use type languages that eliminate whole classes of bugs, like memory safety issues or race conditions. That's a great start. Then now we shrunk kind of what could happen a lot. Then if we use enums or types or other techniques like that, then we make certain states unrepresentable, so we won't have AI generating those bad states for us, right? And then, combining that with, trusted libraries and stuff, we actually limit our losses. So that's a great start, right? Like, this is very basic. But then when we have that, maybe we want to continue towards property-based testing. So you define what is a property that you want. So something that must always hold. So for example, if I have some text, I encode that text into some other format, and then I decode it directly afterwards. It has to be the same text as in the first input. That's a pretty, easy property of a system. But it could be lots of other things. But then if you just write, I have these 3 texts, and I check that encode, decode works on those, and then, that's it. That's my unit test. Then you might be missing a lot of things, right? But if you have the computer, generate all of those kind of example cases for you, then it actually can go deeper into your source code and find the places, the cases that you didn't think about. So that's called a fuzzer or a deterministic simulator that kind of find these, it samples from some random space, tries out a string, sees what happens, right? And there's good tooling here like Hypothesis, Hegel, and GoFuzz, CarGoFuzz, LibFuzzer, and so on. And I really like this quote from Laurie Green. And, well, this is the original one, give a man a fish and you will feed him for a day. but teach a man to fish and you will feed him for a lifetime, right? If we turn this into testing, right, you say, give a computer a test and it might find a bug, but teach the computer how to do the testing for your properties and it might give you just a lifetime of finding the bugs as you do whatever AI coding that you're doing, right? So that's 2. Now 3, going further up the chain. If you have something that is more security critical, then or something that you want to make sure always is correct, then you can use a formal specification language like P, TLA plus, Quint, which is kind of new, TLA plus front end, or SAT. And this is called a model, which is kind of now very overloaded term in the AI space. So, well, then you use a model checker to kind of try all combinations of possible things that could happen up to some depth because, well, you can't run forever because it's exponential search when it's an exhaustive search. But then you can say that up to this depth, my property always held. So I can be pretty sure that, like this is actually correct. And there's lots of these good tools for doing that. But then we kind of come to the final boss of mathematical proof. So now you don't need to rely on, like I tried it, up to depth 10 or 1,000 or 10,000, and it seems to work, right? Now, if you find a way to tell prove that it always works, no matter what the, how many times you're trying it, through, for example, proof by contradiction, contraposition, induction, these kind of things, then you can get a whole new level of rigor, right? What you need for this is a small trusted kernel that mathematically checks that every step that you give it follows from the previous step. So you build from small kind of base assumptions, you build the further proof. And there's a correspondence that says proofs are programs, which means that, well, in this case, LLMs are getting pretty good, surprisingly, at writing these proofs as well. So I really love this picture. We were thinking about how to visualize, proving something from base assumptions. So you have your axioms, you start somewhere, and you walk, you have a really, the path towards the goal, proving the theorem, is not linear, right? And this has been limiting, that only experts can do this, formal verification so far, because walking this route is uneconomical. Some people can do it, but not everyone can afford it. Now, if you have AI, which is pretty good at, doing grunt work, find that, and every time it goes a wrong path, Lean in this case says that, you can't do it because it violates this property of mathematics. Then you have this feedback loop, and it turns out LLMs are pretty good at feedback loops, right? Reinforcement learning. So then you might actually just end up at your theorem. So I tried this, and it's pretty exciting, actually. And it collapses the kind of effort needed significantly. And you can trust that proof because Lean just checks that everything is consistent with the axioms of mathematics. And further, there's already MATLib for Lean, and there is lots of theorems formalized. Now people just started formalizing base kind of functionality in computer science as well, like maps and lists and stuff like that, properties about those. So now you will actually have a toolbox of like all the things that you need for your journey towards the top. Now, as one of the famous mathematicians said, Terence Tao, that sometimes actually getting to the top of the mountain, like getting to prove your goal, like my code is for having this property, is not. I mean, it's great if you can do it, but sometimes the more important part was figuring out something in between there, like building something that others could build upon further because that was more valuable than the end state. So that's something to keep in mind. Then specifications are great because at the end of the day, like in the beginning, you start at day one, your specification, it matches the program perfectly. Over time, when your code has seen production for 1,000 days, your program doesn't really look like you intended, and it's just maybe diverged from the spec that you thought it's doing actually. So there's a couple of things you can use here: ANAS, VRAS, PObserve, to name a few, to kind of bridge the gap between the trainer and the platform in this case and make sure they are consistent. So there's lots of hype around this at the moment, kind of combining deterministic, good old-fashioned AI with non-deterministic LLMs. And the term for this is neurosymbolic AI. If you want to have some terms to Google for, there's lots of new startups in this space. There's formalization of natural language. There's lean models, lean LLMs and stuff like that. And I find it kind of interesting that one of our professors at Alta is actually using these methods to formalize real proofs of mathematics, and has also written some articles. So what does it mean for the cloud native community? It means that, for example, CDAR, which is a CNSR project, already did this. They did it the hard way of having humans write all these proofs. I'm now trying to get the feature I'm working on in Kubernetes to be formally verified as well, as an learning experience. etcd already uses some of these testing methods that we just discussed. But now let's figure out together where do we go next? How can we take this further? And even as much as AI hype and stuff like that we have, I still think human connection, like these communities, diversity of thought will be super important to resolve the problems that we have in our technical challenges that we have. And we really need to think about how do we, if now, I don't know if this will be the case, mathematical proofs and stuff like that, but if it will, how do we get people to upskill to that thing, to not kind of be at the level of writing code? So this might or might not hold true, time will tell. But if the point of this talk was to kind of give a sneak peek of what's happening. If you got excited by this, join the forces, join the community around these things. Because if you want to go fast, go alone. But if you want to go far, go together. Thank you.